for turning in the lab. We can't turn in yet. It's just says quiz and it's empty.
Well, there should be an upload link. Let me take a look. Okay, here. If you click on submit, yes, you're right. Okay.
Yeah,
There was supposed to be an upload link. Let me see what happened.
This is the same lab as a pH and buffer lab, right?
Right.
Okay, good.
I guess it didn't save it. Oh, shoot. I just did something I just realized I didn't want to do. Let me try that one more time. Okay, now it should be okay. I think that's 1244. Just fix it over here too. All right, now give it a try when you get a chance. Was there anything else?
I kept trying to refresh it and it wouldn't, the question wouldn't pop up, so I hit submit. Do you think you can add an extra attempt?
Oh, shoot. Okay. There was only one attempt, the lab?
Yeah.
All right. That should be fixed now.
Okay.
I think.
Here we go. Yep.
Okay, great. All right, we'll take a look at specific problems first, and then we'll go back and look at all the problems. So number 33 here is one of them. So let's take a look at this problem. Okay. So a mixture consisting of 0.150 moles of hydrogen and 0.150 moles of iodine is brought to equilibrium at 445 degrees C in a 3.25 liter flask. What are the equilibrium amounts? So here they're asking for equilibrium amounts, not the equilibrium moles. In this case, you know, when usually I do all the problems the long way, and then after doing it the long way, then you look for shortcuts. In here, I can already see a shortcut. I can see that I could do the ice in moles, and I don't have to do the ice in molarity. And the reason is because I have, if I look, I have 2 moles of substance on the left, and I have 2 moles of substance on the right. And so when I look at the product to reactant ratio, it's going to be two on the top, 2 on the bottom. So if I convert it, let's say from moles to molarity or molarity to moles, the conversion is going to be the same in the numerator and the denominator. And so in this case, I could save time by just using ice in terms of moles. What a lot of people like to do with ice, and your book included, is they like to use millimoles. So for example, 0.150 moles is 150 millimoles. And so they would do it 150 millimoles, 150 millimoles, and then 0 millimoles, and then do the entire ice table in millimoles. So little things like that could save you time. But normally I just do it the long way first, and then, incorporate shortcuts. And you can incorporate shortcuts when you do a lot of these. If you only do like a couple of them, you don't really, see the shortcuts so easily. But after you do a lot of them, some of them kind of start to become repetitive, and you start looking for shortcuts, and the shortcuts just come naturally in that sense. But here we could figure out the molarities of these things. Oops, what happened? Oh, there it is. And so we can get the molarity of the hydrogen. The molarity of the hydrogen, still can't find my calculator, so use my phone here, is going to be 0.150 divided by 3.25. And so just 0.15 divided by 3.25. And so this is going to be 0.0461. Now, this is 3 sig figs, so I'd like to carry 1 extra. And here, I could go millimolar. This would be 46.15 millimolar, but usually I just like to do everything one way. That way, if I have too many variations of units like millimoles, millimolar, et cetera, it gets mixed up. So if I do it the same way, then the numbers, I have a better feel for the numbers, I think. And so let's take a look. The other one's going to be the same. This is going to be 0.04615 molar. And then over here, I'm going to have 0 molar. And so this is just, this would just be a standard Chem 1B stoichiometry problem. If I look at KC is 50.2. So it's not heavily favoring the product. It's not heavily favoring the reactant. And so in this case, I probably wouldn't reset. I might reset. There could be one reason I would reset this. The one reason I would reset this is because I'm going to end up with 2 binomials here. So for example, this is going to be minus X molar, minus X molar. Okay, that's 1 to 1 to 2. So this is going to be plus 2X molar. Here, so I'm going to get 0.04615 minus X. And the same thing here, 0.04615 minus X. I probably would have reset this if, well, actually, there's something else you can see here, maybe, but there's something else that you might be able to see is the symmetry of this particular problem. Okay, yeah, just in the chat, Amina, yes, you just take a picture or PDF. I prefer PDF over JPEG or some kind of picture format. And so if you just scan the calculations via PDF, then that's enough. It should be a very simple lab since everybody already did the calculations, I think. The other thing I see in this picture is I would have reset it if the math, because what I could do is if I reset this, I see that this is stoichiometric. So if I reset this, this would go to 0, 0, and then over here it would be double, whatever the 0.4615 is, it'd be double that. And so that gets rid of 2 binomials and replaces it with 1 binomial. And so it makes the math easier. But in this particular case, the math is going to be easy. I can already see the math is going to be easy because I've seen this kind of problem before. And that is in the numerator, I'm going to have a squared term. So it's going to be 2x quantity squared. In the denominator, these are going to be squared. And so if I have the numerator squared and the denominator squared, then I just take the square root and I don't even have to do the quadratic equation. So here we're going to have the HI concentration at equilibrium squared. That's the product over the reactants. And it's because the reactants are the same here. And so it's going to be H2 times I2 in both of these at equilibrium. And so the math is going to come out easy. It's going to come out 2x quantity squared divided by 0.04615 minus x, okay, times the same. And so this is going to be squared. So I like this. I like it when I have squared on top and squared on bottom, because if I have squared on top and squared on bottom, then it's all I have to do is I'll just take the square root, take the square root of the KC value, and then take the square root of this. And then it goes from a quadratic just to a linear problem here. And so otherwise I might have tried to reset it or do some other tricks, but in this case, this shouldn't be too bad and as far as the math goes. And so it's going to be whatever the square root of 50.2 is. Let's see what that is. So 50.2, take the square root of that, is 7.08. So I'm allowed 3 sig figs, but I like to carry at least one extra sig fig. It's actually not significant, one extra digit to minimize round off error. And this is just going to equal, okay, we'll take the square root of this whole thing. That's going to equal 2x over 0.0461. Okay, this is already one extra digit, sub 5 minus x. And then I'll just cross multiply by this term in the parentheses here. And so I'll take my 7.085. I actually have all the digits in my calculator still. And so I'm just going to use that and just multiply by 0.04615. So times 0.04615 equals. And so this is going to go to 0.3269 minus, okay, 7.085 times x is going to be 7.085, which is equal to 2x. And then I'm going to add 7.085x to both sides. So I'm going to get 9.085x is equal to 0.3269, and then solve for x. So 0.3269 divided by 9.085. 9.085 equals, and so I get an x of 0.035. Okay, how many sig figs? I'm allowed 3 sig figs, so I'll go 359 and then subscript an extra digit, sub 9 here. Okay, then I want the equilibrium amounts. What I'm going to get is the equilibrium concentration. So I could have saved time if I did this by moles, and I could have done moles here because, you know, I have the volume and I multiply it on the top and the bottom by equal factors here. But in this case, I have an extra step I have to do. So the first thing is I need to calculate the molarities here. So this is 0.04615 minus 0.03599. So what does that come out to here? So it's going to be 15 minus 9 is 6, and then 10 minus 1, 5 minus 5 is 0. This is going to be 1, 0. So I get 0.01016 molar here. Okay, this is going to be the same 0.01016 molar here. And over here, it's going to be 2x. 2x is going to be 0.07. What is that? 3599. I have this in on my calculator, so I'll just do it. 0.07198 more. Okay, then I'm going to check my K just to make sure I didn't make any mistakes. I'm going to check the K here. Let's go ahead and check K, which is going to be 0.07198 squared divided by 0.01016 squared. And so I have this in my calculator, square that numerator and then divide it by 0.01016 and then square that, and that equals. And so my calculated K value comes out to 50.196. So I'm allowed 3 sig bigs. So this is going to be 50.2, which checks out because that's what it's supposed to be, 50.2 here. So it looks like I didn't make any calculation errors so far. Okay, now they want the amounts. The amounts are going to be not in molarity. The amounts will be in moles. And so I have to take 3.25 liters and multiply it by the molarity. And so the moles of this will equal 3.25 liters of volume times the concentration of 0.01016 moles per liter. And that gives me how many moles? So 33.25 times 0.01016. 0.01016 equals. And so the moles of this comes out to 0.03302 moles. And that's going to be the same here. And the moles of this will be different. So we'll do this one here is going to be 3.25 liters times 0.07198 moles per liter. 3.25 times 0.07198. That gives us 0.2339. Okay, then we round it to the proper number of sig figs. You know, I always like to show the rounding step, and I'd like you guys to show the rounding step as well. You know, I want to see how you rounded it off. And it's not a bad idea to carry extra digits, especially when we double check it. And so this is going to round to 0.0330 moles here, which is the same for this one here, the iodine, which is, this one's going to round to 0.2. Three, 4. And so these are the amounts. Now, because the moles, total moles of the reactant, and it has to be the same state too, and the total moles of product are equal, then we didn't have to use molarity here. We could have used moles right from the get-go. Now, the problem is let's say if one of these were solid, if this were solid, then it would be different, you know, because we were looking at moles of gas, and over here I just have 1 mole of gas. And so there are potential, you know, drawbacks to taking this shortcut, because if you don't know, you know, that, but it could have saved us a step. So rather than actually 2 steps, rather than calculating the molarities, I wouldn't have bothered calculating the molarities. I would have put 0.150 moles, 0.150 moles, 0 moles, and then minus x moles plus 2x moles, and then 0.50, 150 minus x, 0.150 minus x, and then 2x. And then solve for x. X is going to be different because it's not in molarity. X is going to be in moles, and then calculate the moles here. I would have gotten the same answer here. Okay. All right. Does that answer your question about this particular problem?
Yes.
Okay. Were there other problems that that you want to look at first? I'm sorry, I missed it. No? Oh, 43? Okay, 43. Let's take a look. All right. Cadmium metal is added to 0.350 liters of an aqueous solution in which chromium 3 plus is 1.00 molar. And so cadmium metal, it's solid. Whenever they say like silver metal, cadmium metal, copper metal, that's always solid and there's no charge. It's not an ion, it's just a metal. And so we're going to add it to 350 milliliters or 0.350 liters of an aqueous solution of chromium, 1 molar chromium 3 ion. So this 1 molar. What are the concentrations of the different ionic species at equilibrium? What is the minimum mass of cadmium metal required to establish this equilibrium? Okay, let's take a look at this. So whenever I do a Chem 1B problem, I always set up an ice table regardless. Your doesn't do this all the time, but your book will take lots of shortcuts here, which are fine if you know what you're doing. And then cadmium solid is a pure solid, so we leave that out. Cadmium solid, some of it's going to react. We have to have cadmium there. If we don't have any cadmium, if we had 0 cadmium, then we're not ever going to reach equilibrium. So whenever we cross this out, we assume that we have more than enough or exactly enough. And the Chem 1B stoichiometry we're doing in terms of concentration. If we did this in terms of moles, then cadmium, I'd include moles here because we're doing it. But since we're doing it in terms of concentration, the concentration of cadmium doesn't change. It's not going to impact K here. All right. So they didn't tell us how much chromium 2 and cadmium 2. And so since they didn't tell us how much of these we have to assume that we're starting off with 0 of both of those. And so when we look at the Kc equation here, it's just 0.288, which is going to equal the chromium 2 plus squared times the cadmium 2 plus divided by the chromium 3 plus squared. And then cadmium, we can put a 1 here, but we don't need to. Cadmium's not in there. And so when we look at the Kc, it's 0.288, which says it's slightly favored to the reactant, but this is hard to say. This means it's neither favored the reactant or the product, It's not heavily biased. If it were a very small number, it would be biased towards the reactant. If it were a very large number, it would be biased towards the product. What's a very small, very large? Like 1,000, 1,000,000, billion, trillion to 1, That would be in. But in this particular case here, we could reset this if we want, but I don't see any reason to reset this at all, because here we have a 0 and a 0. There are 2 reasons to reset it. One is we approach the equilibrium from a initial state that's closest to it. Here it doesn't really matter, both sides. Both sides I'm going to have significant reaction forward. If I reset this to the product, I'm going to have significant reaction reverse. So it doesn't really matter. So I don't bother resetting this one. And then we look, it's a 2 to 1 to 2 to 1 ratio. So this is going to be minus 2x molar. Now, if I did this in terms of moles, I wouldn't do this in terms of moles because one, this mismatch is actually there's 2 here, there's 3 here, and then the cadmium. What do we do with that? And so I'm just going to keep it molarity here. And so this is going to be plus 2x molar. And this is going to be plus x molar here. And so at equilibrium, I'm going to have 1.00 minus 2x quantity molar. And then this is going to be 2x molar here. And this is going to be x molar here. Now, what's this going to equal? Well, I'm going to get 2x, that's chromium, and that 2x is going to be squared. And so my concentrated chromium 2 plus at equilibrium is 2x. We'll put that in there. The concentration cadmium is just x. And concentration chromium 3 plus is 1.00 minus 2x. And then I'm kind of disappointed here because I can't take the square root. The square root worked brilliantly for the last problem, but this x is throwing it off. If I didn't have this x sitting here, I could have taken the square root. But this is going to end up being a cubic equation. And so, my calculator could do cubic. So we could get this into cubic form perhaps. And this one might not be too hard to get into cubic form. So maybe we'll just try to solve this one without any tricks. Let's see if we can just solve this normally. And so I got 0.288, and then this is going to be 4x cubed on the top, 4x cubed. And then on the bottom, I'm going to multiply this binomial out here. And so what does it come out to? It's going to come out to 4x squared, right? Minus 2x, minus 2x would be what? Minus 4x plus 1.00. Is that what you guys get, you math people? Okay, I'll take that as a yes. And then we'll go with, I'm going to multiply, the denominator here by 0.288. So let's try that. So 4 times 0.288 is equal to 1.152. So I'm going to put everything on the right side. So I'll put the right side on the left side here. So I get 4x cubed, and this is going to be minus 1.152 x squared. Okay, then I go 0.288 times minus 4x. And so that's going to be plus 1.152x, and then 0.288 times 1, and then subtract it. And so that's going to be minus 0.288 is equal to 0. Now, do you have a calculator that can solve cubic equations? Well, you know that Casio can. And so, but if you're doing homework, you just go to cubic equation solver. Cubic equation solver. Just use a cubic equation calculator here. So let's see what those were. Those numbers were 4 minus 1.152 plus 1.152 and 0.288. I doubt I'll remember that, but let's see. I'll move it over here so I can see it. 4. And the other one was. So if your calculator can solve cubics, then you can just plug these numbers into your calculator. Minus 1.152. C is going to be plus 1.152, and D was 0.288. Actually, minus 0.288. Calculate it. Okay, so we got through 2 imaginary, 1 real. So we'll just take the real x3 here. X3 is 0.25709. So 0.25709. All right, let's try it and see what we get. And so for the chromium 3 plus concentration, it's going to be 1.00 minus 0.25709. And so what is that? I don't want to do it in my head, so I'm just going to do 1 minus 0.25709. I get 0.74291. 74291 molar. We're allowed how many sig figs? Three sig figs. Okay, the chromium 2 plus is double this. So what is 2 times 0.25709? 0.51418. So this is 0.51418 molar. I'll carry 2 extra here. And then this is the same 0.51418 molar. Okay, I want to carry extra digits because I want to double check my K here. So let's double check the K value. And so it's going to be this squared and this to the first, actually. Now, one thing that people get confused with is this. Take a look here. I have this 2 here. Does this 2 mean I have to double this concentration here? Yes or no? Does that 2 mean I have to double this concentration here? Yes or no? Yes? Yes? Actually, no. Sorry. This 2 means I don't double. The 2 means I double X. Didn't I just double X? Yeah, what was X? X was 0.25709. So if I double this, then I'm doubling it twice, right? So here, this 2 means I double X, which was 0.25709. I just did that and I got 0.51418. I don't double it again when I plug it into this equation here. What I'm going to do is I'm just doing this. I see this mistake. I have this is the concentration of the chromium 2. The concentration of chromium 2 I plug into this equation. This number does not go into this equation. This number goes into this equation here. This number goes into this equation here. Oh, okay. Yeah, you're right. I made a mistake there. Somebody caught my mistake. This is X. This is not 2X. This is just X. And so this is wrong here. I would have, you know where I would have caught it? Fortunately, I would have caught it during the double check here. You know, this was to illustrate the double check failing. If the double check fails, then I know I made a mistake somewhere, you know, and so this is kind of where hopefully I would catch it, but you caught it earlier than the double check, which is good. And so the concentration here is X, not 2X. So this is going to be 0.25709 molar here. Okay, so now let's check our calculation. So to check our calculation, this is going to come out to 0.51418, and it's going to be the chromium 2 plus squared. So we're going to square that. And then the cadmium 2 plus is just to the first power. So this is going to be times 0.25709. And then we divide it by the chromium squared. So this is the chromium here, and we're going to square that, 0.74291 squared. And so let's see, you know, it could have made another mistake, you know, it happens. And so it's just good to catch those mistakes.
Professor?
Yes.
For the, I think it's 1.00 minus 2 times X, not 1 minus X.
Yes, you're right. You're right. That's another mistake. That's another mistake. Let's see if K would have caught that. And so let me just finish this here and see what my K value would have come out to had I not caught that mistake. And so had you not caught that mistake, 25709, 25709 divided by 0.74291 squared. Okay, so my K value would have come out to 0.1237. My K value is supposed to come out to 0.288. And so this is not within rounding error. You know, sometimes you can say, oh, that's within rounding error. But here it's definitely significantly different. And so it looks like you caught the error here. Hopefully that was the last error I had made here. This is not minus X, it's minus 2X. 2X is 0.51418. 51418. Which is going to change this molarity. So it's going to be 1 minus 0.51418 is going to come out to 0.48582. 48582. This is more. I'm only allowed 2 decimal places here because it's 1.00. So I'm carrying 3 extra digits here, but I want to carry 3 extra digits just to see if my K comes out closer. Okay, so let's do K again. And so this is going to be 0.48582 squared. And this is going to be 0.25709 divided by, whoops, screwed that up. This should be in the denominator here. These should be in the numerator here. Yeah. So let me just do it this way. 25709 times 0.51418 squared. Okay, so try this now. I have the denominator in my calculator, so I'm going to square that and then invert it, and then times 0.25709, 0.25709 times 0.51418 squared. Okay, and what do you guys get? Well, I got a weird number. I got a negative number, which tells me I did something wrong with the calculator. So I'm going to just do it one more time. 0.51418 squared times 0.25709 equals divided times 1 divided by 0.48582 squared. Okay, so when I do this now, I get 0.2879. This is going to just round. This is going to round to 288, and so that looks good. So I think we're good here, and then we'll just go ahead and round to the correct number of sig figs and decimal places. So here I'm only allowed 2 decimal places, 0.49 molar. Correct number of decimal places for that. Over here, this is going to be 3 sig figs. Yeah, 3 sig figs. So this is going to be 0.514 molar. And here, this is 3 sig figs, 0.257 molar. Okay, again, I don't like to calculate K with the rounded values, because then the rounded values could mean it comes further off. And so if I calculated K with the rounded values, what would I have gotten? And so let's take a look. That's to see how far off it would be due to rounding error. And so I'm going to go 0.257 times 0.514 squared divided by 0.49. Oh boy, can't be. I screwed up the calculator again. I got to find my calculator. This phone is not so easy to hit the buttons. The buttons are so small. 0.514 squared times 0.257 divided by 0.49 squared. I still not getting the right. What did you guys get for if the blue? If we use the blue concentrations, what do you guys get? .288, 0.1385, that far off? Is that what other people got? I got 0.0747, but I'm thinking that's got to be wrong. Let me try one more time. 0.514 squared times 0.257 equals divided by 0.49. 0.49 squared. Yeah, I did 0.282. 0.2827. And so this goes to 0.283. You might say, well, 0.283 and 0.288 are close enough. You know, that's possible. Or you might go, well, it's, you know, it's just this in the back of your mind. Is it, you know, close enough? Or could it be closer? And in fact, it's the exact same calculation. It's just rounding. That's it. And so this is why I'm in the habit of carrying extra digits until the very end, because I want to double check, and I don't want rounding to cloud, you know, or to give me second thoughts. You know, why is it off? 283. It's supposed to be 288. Why is it off? Did I make a simple error? You know, and so I don't want to have that cloud hanging over my head with this. All right, now let's say you don't have a fancy calculator that can solve cubics. Then what would you do in this case? Would you try the simplifying assumption? So let's say I didn't have a fancy calculator, and I'll try one of the tricks in the book. And one of the tricks is, okay, let's say alternatively, would alternatively try the SA. SA just stands for simplifying assumption. Okay, we'll go ahead and try the SA. So if I try the SA here, I would just say, okay, let's go ahead and say that the change is small compared to the initial. Here we can't say the change is small. You know, there's no change, it's 0, you know. And so we keep these. So this is going to be 4x squared times x would be x cubed. And then we do 1.00 minus 2x is 1.00. And then we'll just square that. We just get 4x cubed. When we solve for x, well, the math is easy here because x cubed is 0.288. So we'll take 0.288. 0.288 divided by 4 equals 0.072. And then we'll take the cube root. This calculator has a cube root, which is nice. So I'll just do cube root 6. And then I have to justify the simplifying assumption or validate it. And when I calculate the percent change here, the percent change is the change, which is 2x. So 2 times this is 0.832. So 2x is the change, which is going to be 0.832 over my initial. My initial is 1.00 times 100%, which gives me an 83.2% change. Unfortunately, 83.2% is larger than 5%. 5% was our cutoff, and so the essay fails. So what do we do then? Maybe we try resetting it. Actually, resetting it won't do no good. Resetting it won't do any good because it's not heavily favored on the left nor the right. Resetting it would be great if it were heavily favored on one side or the other. But in this case, it's not a very, very small number like 10 to the minus 6 or 10 to the minus 9 or 10 to the minus 10. And it's not a very large number like 10 to the 10. So resetting it won't do any good. So are there any other tricks to try? Yeah, unfortunately, reset. If we try to reset this to the right, the same thing's going to happen. There's going to be a significant change to the left. And the significant change to the left means the percent change is going to be too huge. And so reset will fail. I could try it and see that it fails. And this is a good thing to do is you try, you try it and see what happens. But I'll tell you what's going to happen. We reset it, the same thing's going to happen. The percent change is going to be too huge. Yeah, and so we're left with a guess and check. And so here you're going to just start doing the guess and check method. But what do you use as your first guess for X? What would you use for your first guess for X? Well, one thing you could try is, you'd use the X value that we might have calculated. We can't use this one. We can't use this one here because we got this from the cubic equation solver. And if you don't have the fancy calculator, then you don't have the cubic equation solver. And so we're going to have to come up with another X value. And so what would you guess for X? Here you could have taken some random guess. You would guess that it's like maybe 50-50. So you just take off half of that. So you get an X of about a quarter. A quarter and double that gives you half. And if we say it's about 50-50 because, this is close to 1, then maybe that's okay. And so X at 0.5, but I mean 0.25, then we would have been very close. Do you see that? Very close. If we did, let's say if we did the simplifying assumption to get our X is so far off. Look we'd be starting at 0.4. Maybe we could get there quickly. I don't know. But guess and check, the initial X might be hard here because it might just be a random guess. But here you can use the K here to try to figure it out. That it's going to be significant quantities of both reactants and products. How many of you guys solved this one? How did you solve it? What did you use to solve for x? Did anybody do number 43?
I got to the cubic equation and then I got stuck.
Okay, well, with the cubic equation, you're allowed a cubic equation solver. You know, if I had my TI, I could show it to you. It's pretty simple. Do you have that calculator?
I have the TI 84 plus silver edition.
Does that have polynomial solver?
Possibly.
Silver edition. See the specs on this. Yeah. Polynomial root finder. Simultaneous equation solver. So yeah, this would work too. You could just solve it using this. Is this okay for the SAT?
Yeah, I'm
Yeah.
pretty sure.
Yeah, so this would be okay. You'd use this calculator. So this is a good calculator here. Just learn how to use the, wow, it's expensive. Is this programmable? Yeah.
Mine wasn't nearly that expensive. I think that's a slightly different
It's
one.
programmable like that, but I have no idea how to program it.
Okay, well, programmable calculators aren't allowed. It's okay. Yeah,
I literally have no idea how to use that
okay.
function of it.
Yeah, me too. I don't. I have a very simple calculator.
That's how I use mine, just as like a relatively simple calculator.
Yeah. It's also nice to have a simple calculator as a backup calculator. This calculator is really powerful. This Casio FX 115 ES plus 2. Well, it's only 1550. The price has gone down. Or 2 for 45. I think this one does it. Yeah. If you were to do the guess and check on that previous problem, the only worry is if you guess an X that's far off, and then it takes you a lot of guesses. So sometimes I see, like when people are doing guess and check, like on a test or something, I see them do like 2 pages worth of guesses, and then they give up. With the guess and check, eventually you just have to have a lot of perseverance and patience to do it, to try to get it to converge. But they're getting very frustrated at that because it wasn't converging. And then if it's some funky polynomial function, they could hit a minimum, you know, and get stuck. And so the closer you are, the easier it is. The further away you are, you know, they're getting frustrated because it's going up and then went down and then up and then, you know, it was getting hard to figure out. And so here in this particular case, I would have guessed, well, it's going to be about half and half, let's say close to 1. And so if I lose about half of this, you know, 50% reaction, then that's going to be about 0.5. And then take half of that for my X. And so X is equal to 0.25. And then we would have been very close. Okay. So you tried Invictia and you got stuck? What was your first X guess? I don't know what the book recommended for solving this particular problem. Okay, were there other problems that you want me to look at first? You know, this is since this is a homework, we could just figure this out. You know, this is going to be 4x cubed, 1 minus 2x quantity squared. And so we figure this out. Just figure this out using Excel. And so we'll just make up a formula here. Formula is equal to, we're going to do 4x cubed. So x we're going to call a, it's this cell here. And then we're going to cube that. Let's see if that works. Divided by, let's see, 1 minus 2 times x. So let's plug in, just say 0.5. This is some guess. What happened to my formula? Why is this not? Okay, that's working. Okay, now it's working, I think. So we can try guessing and checking here. So I have my formula here. I'm just going to have Excel do the calculations. So we can't have 0.5. If x is 0.5, this is going to go negative, or actually this is going to go 0. So 0.5 times 2 is 1, 1 minus 1, 0. We can't have that. So it can't be greater than 0.5. So it's got to be between 0 and 0.5. So we can try 0.4. If we tried 0.4, we got 6.4. And then we could try 0.3, we got 0.675. And then we could try 0.2, and then we got 0.088, and then we could try 0.1. And then, what should we try? Here, it looks like it's got to be between 0.3 and 0.4 because we need it to equal 2.88, right? Or 0.288, actually 0.288. 0.288 is going to be between 0.2 and 0.3 right here. So we try 0.25. And we're getting closer because we get 0.25, which is getting closer. And so we'll try 0.26. Now we're getting farther. And so we'll try 0.255. Now we're getting closer. And so we'll try 0.256. Closer. 0.257. Closer. Almost there. 0.258. Too far. Back off. 0.2575. A little bit too big. 0.2574. Almost there. 0.2573. 0.2572, 0.2571. There we are. And so 0.2571, how many guesses? Obviously, this takes some time to calculate, but how many guesses did that take me? 1, 2, 3, 4. I'm gonna count here. Oops. Come on. 10, 11, 12. What happened? $15 guesses. So in 15 guesses, and you're punching this in the calculator. So how long does that take? 30 minutes, 20 minutes in class? So. All right, so these would have been the guesses I would have taken. These are random guesses, and we can't go above 0.5, so kind of limited it. I had no X value, and so I didn't use this X value here, 0.416. If I did 0.4, it comes out 6.4. It's way off. That's because the essay is way off, and so this was just total random guessing here. Okay. Does that answer the question for number 43? Yeah? No? All right, other questions? Not entirely. Okay, what else do you want to know about this, or what? Oh, there's 2 questions. What is the minimum mass of cadmium metal required to establish this equilibrium? All right, so this is just going to be straight stoichiometry. We have to have enough cadmium metal. And so this is how we can figure out how much. Now, we have to get comfortable working with molarity and moles, that kind of stuff. Now, in Chem 1B stoichiometry, we're always using molarity. But if we want, molarity is just a ratio. But if we want the actual amounts, we need the volume here, 0.350 liters here. And so what we can do is we can just use regular old stoichiometry to figure this out. And so how much cadmium is going to be consumed? So it's going to be minus 2x molar, but we're also going to lose minus some number of moles of cadmium. And so over here, we have to have that bare minimum. And so whatever this is here, whatever this is here, we have to lose some here. We have to make sure we have enough cadmium to react with that. And so how much did we lose? What is minus 2x? Well, minus 2x here is this, minus 0.51418 molar. That's how much we lost. And therefore, we have to have enough cadmium to react with all of that in the 2-to-1 ratio. All right, so this is the way we can do it. We can just use regular Chem 1A style stoichiometry for this particular problem. And so I am going to lose 0.51418 molar chromium 3 plus consumed. All right, that's molar consumed, but how many moles were actually consumed? Well, it depends on the volume. If I had a liter, it'd be 0.51418 moles if I had a liter, but I don't have a liter. I only have 0.350 liters. So what I'm gonna do is I'm gonna just multiply this by 0.350 liters of solution times this. That's gonna give me the moles of chromium 3 plus. And the moles of chromium 3 plus, I need to figure out how many moles of cadmium 2 plus that is. And so we can just do that based on the mole ratio. It's a 2-to-1 mole ratio. So 1 mole of cadmium is consumed for every 2 moles of chromium 3 plus consumed. And then I need the molar mass of cadmium. And so I got to figure out what is the molar mass of cadmium. And so I need the periodic table for that. Let's get the periodic table. Just had a periodic table. Where did I put it? Let me find my periodic table. Actually, this is, I have a periodic table on my computer, but I'm not gonna bother with it. Unless, do you know what the molar mass of cadmium is? $112.411. There are some molar masses I have memorized, but not cadmium. And so this is going to tell us how many moles of chromium-3 were consumed. And then based on the mole ratio, we can figure out how many moles of cadmium were consumed. And then we can convert that to grams of cadmium here. And so I'll take 0.35 times 0.51418 moles per liter of cadmium. I mean, chromium 3 plus divided by 2 times 112.411. 10.11. And so in reality, I wrote a line through this, but in reality, I'm going to lose minus 10.11 grams. And that means I have to have a minimum of 10.11 grams at the start. So I have to have greater than or equal to 10.11 grams. Otherwise, the chromium is not going to all react. And so this has got to be this is going to be the limiting. Well, I have to have excess reagent here. And so if I just had 10.11, then I'm going to end up with 0 at equilibrium. And so I probably want a little bit more. So I have some excess cadmium at equilibrium. Okay, does that answer the question? Yeah.
Yeah.
Okay. All right, great. All right, was there another question? Okay, let's go back here and let's take a look at the problems. You tell me, were there any problems with number 1? So I signed this, writing the KC. Was this pretty straightforward, or do you want me to go through this number 1? Some of these might have been a little weird. So let's talk about some of these, especially I got some questions about the ratios. And there's certain things that can help you with the ratios here. Actually, let's do number 1 and number 2 together. We can do these quickly, I think. So, for example, 1B, A lot of people, well, they're saying copper metal. Copper metal is always Cu solid. Displaces silver ion. So silver 1 ion. Normally we don't need this Roman numeral. Silver only has 1 charge. If silver only has 1 charge, then we don't need this Roman numeral. I don't know why they wrote the Roman numeral there. Nobody ever calls it silver 1. Everybody calls it silver ion from aqueous solution producing silver metal. So silver metal is Ag solid and an aqueous solution of copper 2 plus, Cu2 plus. And so this looks balanced, but it isn't. And so there are 2 ways you can tell it's not balanced. One, just by looking at the total charge on the left and the total charge on the right. Total charge on the left, copper and silver are neutral. So the total charge is +1 on the left and +2. There's a mismatch of charge. The charges aren't balanced. That's one way. Or 2, if you know what we call the half reactions. The half reactions, this is discussed in chapter 5, I think. And so when we look at copper goes to copper 2 plus, copper solid goes to copper 2 plus. And then what has to happen is there has to be 2 electrons lost. This is what we call oxidation. Oxidation is loss of electrons. And so we call this the oxidation half reaction. Okay, whereas silver ions must gain an electron. Okay, so silver ions gain an electron to form silver metal. Okay, this is called the reduction half reaction. And so this brings up this thing called oil rig. Oil is oxidation is losing electrons. So oxidation, and then rig is reduction is gaining electrons. So reduction is gaining electrons. But the situation is the number of electrons that we lose must equal the number of electrons that we gain. And this is not the case here because we lose 2 electrons and we only gain 1 electron here. So there's a mismatch in electrons here. We can't have that because we can't have leftover electrons. And since we can't have leftover electrons, what we have to do is we have to multiply this one by 2. We have to double it. And so the other way we could tell that this isn't working out is by oxidation states. Or actually there are 3 ways, the half reactions, the total charge, or the oxidation states will do it. And so looking at the oxidation states, this is 0, this is +1, this is 0, this is +2. So to get from copper 0 to copper 2 plus, we lose 2 electrons. However, to get from silver ion to silver, we gain 1 electron. And so we see this can't work. And so we have to double the silver. All right, for C, 1C is a little bit more complex because of this. Have you seen peroxodisulfate ion? Peroxodisulfate ion, yes, we've seen that. Peroxodisulfate is a very unusual ion, but you might recognize it. Where have you seen peroxodisulfate before? Can somebody remind me where we might have seen peroxodisulfate before? Cleaning supplies, it would be pretty dangerous cleaning supplies if you use peroxodisulfate in your cleaning supplies. Let me see. Is it a good reducer on the react? No, it is not a good reducer. It's not a good reducer. Where's my redox chart? I can't believe I don't have a redox chart here. Let's see, I'm gonna search it. It's not a good reducer. It's here. You might think it's a reducer because it undergoes reduction, but if it undergoes reduction, it's an oxidizer. It's a very good oxidizer. In fact, it's number 3 on the chart. Third most powerful oxidizer on the chart. And so this is it. Anyway, peroxide disulfate requires 2 electrons to react to form the sulfates. Powerful oxidizer. The sulfur is +7, which is very unusual, but it's not really +7. It's due to the oxygens because of the structure. Maybe I'll talk about it later. And so here we can figure it out. Peroxide disulfate requires 2 electrons. And so here, probably the half reactions are maybe the best way of determining this. And then we have iron 3. I mean, iron 2 goes to iron 3. And so there's a mismatch in the electrons again here. 2 electrons are required for the peroxide disulfate. And if we look, only 1 electron is produced. And so we need to double this one. Alternatively, when we write out the equation here, we'd see the total charges don't match. And then we can just guess, we can just double it or do whatever with that. All right, and then we looked at number 2. Oxygen gas oxidizes aqueous ammonia to gaseous nitrogen and water vapor. And so here, you can just take a look at this. O2 gas oxidizes. So this is an oxidizer, gaseous ammonia. Ammonia is a reducer. Ammonia is a good reducer to gaseous nitrogen and water vapor. So there's no charge here. So all we have to do is atom balance this. And so 2 oxygens, that means we need 2 waters. Because 4 hydrogens. This is actually not going to work so easily, unfortunately. We'll leave the nitrogens. We're going to have at least 2 ammonias here. We'll give us 2 nitrogens there, 6 hydrogens. So we'll need 3 of these. And then if we have 3 of those, then we need 3 oxygens. So we'll take 3 halves and then just double everything. So we get 3 O2s plus 4 NH3 yields 2 N2s plus 6 H2O. Let's see if it's balanced here. So 6 oxygens, 4 nitrogens, 8 hydrogens. Oops, it's not balanced. Oh, this is 12, sorry. 12 hydrogens. Now it's balanced. And these are all gases, then we can come up. So this is like Chem 1A. This is just equation balancing. And then, so they throw this kind of stuff in so you don't lose practice with equation balancing. And then this is Kp, so it's pressure of N2 squared, pressure of H2O to the 6th, the pressure of O2 to the 3rd, and the pressure of NH3 to the 4th. So that would be the Kp. So that's like number 2. Let's see what time it is. We'll go, it's another 10 minutes or so. Hydrogen gas reduces gaseous nitrogen dioxide to gaseous ammonia and water vapor. So this is oxidation. So essentially we're trying to burn the ammonia, but this is very clean burning. Boy, normally when we burn ammonia, we form NOx, NOx. Poisonous gases. If you could burn it like this, then you just form nitrogen. Nitrogen's non-toxic. Water is not toxic unless you have too much of it. Nitrogen can be toxic if there's no oxygen. But boy, this is a clean burning. And so if you try to do this in the lab, you're probably going to generate lots of toxic NOx gases. If I tried to do this in the lab. So if I tried to burn ammonia with air or oxygen, I'll probably end up with lots of NOx. you end up getting mixtures of things, and redox, things kind of get complicated, and sometimes things you hope would work out like this, burning it to get nitrogen and water and heat, this would be good. Doesn't always work out. B, hydrogen gas reduces gaseous nitrogen dioxide. Hydrogen is a great reducing agent. A reducing agent is electron rich. And if we have nitrogen dioxide is one of these NOx that we worry about inhaling, the poisonous. So we'll take hydrogen and NO2, and we're going to go to gaseous ammonia, H3, and water vapor, H2O gas. It's hard to predict, if I burn ammonia, it's hard to predict what I'm going to form. I could form multiple things. So these are examples of skeleton redox. You just burn it and see what happens, or you try to reduce it. In this case, we're going to burn the hydrogen using NO2 rather than O2. Normally, when we burn hydrogen, we use O2, but we can use NO2 because NO2 should be an oxidizer. You look at nitrogens in the +4, almost +5, which is its max. And so here we're going to burn hydrogen with NO2, but what do we form? We're going to form NH3 and water. Or reduce, we'd reduce it, because this one is going from +4 to -3. And so this is being heavily, normally we just go to nitrogen, maybe, let's say. But this is gaining 7 electrons here. Anyway, we just balance this and then get the gases. Nitrogen gas reacts with solid sodium carbonate and carbon to produce solid sodium cyanide and carbon monoxide gas. Boy, and so this one's not balanced. The way we balance, let me just give you a little refresher for balancing. Maybe we always save the single element for last, and that makes balancing a lot easier. And so here I have one nitrogen, that's okay. I have 2 oxygens here, I'll need 2 waters. That gives me 4 hydrogens here. And then I'll just have 2 here. Well, that was easy to balance. C, a nitrogen gas reacts with solid sodium carbonate. So N2 is very unreactive. So this is a very interesting reaction. Solid sodium carbonate and carbon plus carbon, solid, to produce solid sodium cyanide, and carbon monoxide gas. So this is solid. All these are, this is solid. We have 2 gases here. And so 2 sodiums, gives me 2 nitrogens. Well, that's what I want to do here. 1, 2, 3. How many carbons? 1, 2, 3 carbons. So we'll add 2 there. And then figure it out, etc. So it just takes time to balance it. And then we can do the KPs. KPs, their only gases here would be these and this. Actually, ammonia is a gas. These are all gases here. Here, we only have this as a gas and this as a gas. And so just these 2 are going to appear. And so this partial, well, I don't know what the coefficient is. Maybe 2, 1, and 1. To square it. Okay, we'll go till 11:30. I'm going to go through a series, let's say 7 BC. Go through a series of these. We'll just go through probably all the problems. And so today we'll go here 10 maybe to 11:30, a little bit longer. And then tomorrow we'll have another session. So tomorrow, probably the same time, 10 p.m. to 11:30. It'll be recorded, so if you can't make it, that's fine. And then maybe since exam's coming up, maybe we'll just do it every night to the exam. And then we can finish the homework early. If I don't talk too much, we can get through the homework pretty quickly. Although there's a lot of problems there, so it takes time if you haven't done these before. All right, so let me finish off with 7BC here. 7, determine KC and the KP values given. So we're given KP, we just need to calculate KC. And we just need delta N of gas. And so this is just using the equations. So once you familiarize yourself with using the equations, it's fine. So 7BC 80, let's take a look at those. So KP is equal to, now this equation, KC RT to the delta N of gas. So we're solving for KC. Okay, so that means KC is going to equal 1.48. Let's get KP times 10 to the 4th divided by RT. R is 0.08206. Now, do we do it in liters? I mean, atmosphere or bar? I only know atmospheres. This is liters atmosphere per mole Kelvin. If I need to convert it to bar, I'm going to multiply it by 1.01325 bar per atmosphere. This is bars per atmospheres. The atmospheres could cancel, but I'm not going to write out all the units because the units don't cancel here, regardless, as you normally would expect. And then T is 184 degrees C plus 273 would be to 357 Kelvin. The Kelvin cancels out. Atmospheres, well, actually, what would the units be here? This is liters atmosphere per mole Kelvin. So the atmospheres cancel. The moles don't cancel. Kelvin cancels. So I get liters bar per mole. Liters times bar. This is joules. This is work per mole. Work per mole. Well, anyway, we don't have to worry about the units. So let's ignore that and then calculate it. But what is our delta N of gas? And so can you see? What is our delta N of gas for this particular problem? Yeah, -1. So we go 3 to a 2, it's -1. So I can just bring it to the top and then just multiply it out. So this is going to be very similar, except the delta N of gas is going to be tricky because of the solid here, and the solid here. What's the delta N of gas for this one? C. I think I already did these in class. 0. 0 is correct. 8. What's the delta N of gas for this one? +1. Okay, good. All right, so, and then just plug it into this equation and then do the calculation. Then it should be okay. We're assuming that KP is in bar. That's why I have this 1.01325 bar per atmosphere. Okay, so we'll stop here and then we'll do another session tomorrow at 10 p.m. If you can make it. Can you guys make it? Or do you want an alternate time? Let's see. I don't know tomorrow's schedule. Can anybody make it tomorrow? Okay. All right, then we'll do it tomorrow at 10 p.m. then, if that works for you guys. Okay. All right, we'll see you then tomorrow, and then I'm going to try to get through. I don't know how much of these homework problems you guys have done, but we'll try to get through these with some maybe explanation to these. So we've already taken care of some of these. Okay, were there any other questions?
Yeah, I had a question, not about the homework, but the
Okay.
exam. I was wondering if we were going to go over the format of the exam.
Yeah, the format of the exam is going to be multiple choice with some free response. I haven't completely determined the format yet, but the format of the test will be like, I'm not sure if I'm going to make it longer than 1 page. But you'll have a number of multiple choice questions. Let's see. And then you'll have some free response, like calculations. But the multiple choice questions can involve calculations as well here. And the free response will probably be calculations for this particular chapter. So let me see what I have here.
Also, will we get some kind of equation sheet on the test?
Some constants like R probably. I don't know. What equations were you looking for?
Maybe like the pH stuff.
You aren't going to have pH on this test.
Oh, okay.
Maybe something like this.
Okay.
So here you're going to have some multiple choice. How many multiple choice questions have I put on? I've had 15 multiple choice. It's only 1 page test. The 15 multiple choice, some of these involve calculations. I think this one involves a calculation here. The others are just conceptual. This one involves a calculation. There's a calculation here. And then 2 free response questions here, it looks like.
Okay. So it'll be on chapter 24 and then 15 through 17?
No, only chapter 15.
Oh, okay.
24, I'm going to test on later, I think. You know, when I give a test on 24 early, I don't know if this is going to work or not. I was thinking maybe it's just because people, you know, some people do very well with that nomenclature. Some people do very bad on the nomenclature. So I was thinking I'll try to improve the very bad scores by maybe giving people more chance to, because we're dealing with complexes the entire semester. And so I was thinking I'll test the nomenclature near the end of the semester rather than right at the beginning. And so hopefully that improves the very poor scores that I will usually see with nomenclature. But we'll see if that
So it'll
works.
pretty much just be equilibrium.
Yeah, only chapter 15. And then the chemical reaction stuff, you know, that I was thinking just get more practice. So that will be tested near the end of the semester, not at the beginning. So we have more opportunity.
Okay, thank you.
If you look at some of these, like if you look at number 17, take a look at number 17. Does this one look familiar? Well, kind of, you know. We did a problem similar to this. Not exactly the same, but similar. Some of these are a bit more tricky here. You know, I did talk about KP, KEQ, and KC. You know, and so let's try to answer number 4 here. For the reaction in 3, KP equals KEQ, which does not equal KC. Is that true or false? I'll take a look over here. What do you say? KEQ for gases is KP. If they're all gases. In this case, this kind of qualifies as all gases because this is liquid and liquids don't show up, you know, the water. And KEQ, if these were all aqueous, would be KC. And so KP is equal to KEQ, that's true. So the second part is KEQ and KP the same as KC? So is KP and KC the same thing here? So we were just talking about KP and KC. KP and KC are only equal when delta N of gas is equal to what? KP and KC are equal only when delta N of gas is equal to 0. Is delta N of gas equal to 0 here? What is delta N of gas for number 3? Yeah. Delta N, and so number 4 is actually true. Is KP and KEQ are the same because it's gas and this is liquid, there's no solution there. Which is not equal to KC because in order for KP to equal to KC, delta N of gas is equal to 0, but here it's -2. We start off, or -3, we start off with 3 moles of gas and go to no moles of gas. So we lose 3 moles of gas because we end up with liquid here. And so true. Answer. We could take a look at these too. You know, might as well take a look at some of these right now. Calcium carbonate solid goes to calcium oxide solid plus CO2. This, remember this equation? This is one of the most significant reactions in modern civilization. Removal of CO2 shifts the equilibrium which way? To the right, correct. That's correct, good. Determine the value of Kc for this reaction. 1/2 N2 plus 1/2 O2 plus 1/2 Br2 yields NOBr gas using the data below. So this is like Hess's law. The way I like to do Hess's law is I like to get 1/2 N2 over here. So to get 1/2 N2 over here, I got to take this one and reverse it. If I reverse this one, then that flips this. So I flip this. And then I got to multiply by 1/2. So I reverse this one and multiply by 1/2. That means I take the square root. So invert this and take the square root, and that gives me 1/2 N2 and 1/2 O2 on the reactants. But it also gives me NO on the product. I don't want NO on the product. But I also need a 1/2 BR2, so I'll just add this one, and that gives me my NOBR. And so I invert this one, which would be, let's say 2.1 times 10 to the 30th. 2.1 times 10 to the 30th equals, invert that one, and then take the square root, because I'm multiplying by half, then times 1.4. And I get 9.66 times 10 to the minus 16. So 9.66 times 10 to the minus 16 rounds to 9.7 times 10 to the minus 16. And so I get this. The units of Kp for the reaction 2H2 plus O2 yields 2H2O liquid are, do we have units on Kp or Kc or Keq? No, so that's dimensionless. There are no units. So we already did number 4, we did number 4. So the test is going to have a mix of conceptual questions and calculations. Because, sure. I was looking at some of these questions for some of the standardized exams. And they're pretty, they give a lot of information, you know, and so it's easy to get confused. And so I don't put in a whole bunch of extra information there, but you have to watch out for that because, you know, you might have a standardized test that you have to take. How about number 5? The equilibrium CO2 plus H2 gas yields CO plus H2O gas depends on volume. What that means is the volume will shift this one way or the other depending on if I increase the volume or decrease the volume. How, in this equilibrium, if I increase the volume, which side is favored? The left side or the right side? Okay, you're saying the left side is favored because why? If I increase the volume, you want to favor the side with more moles of gas, but when I look at the left side doesn't have more moles than the right side. In fact, both the left side and the right side are equal. And so you're right, neither is favored. Neither side is favored. Because we're just looking strictly at moles of gas. So the coefficient's 1 and the coefficient 1. So left side has 2 moles of gas, right side has 2 moles of gas. And so since we have both the same number of moles of gas on both sides. So the volume would favor the one with more moles. Yeah, the larger the volume, if it was different, but in this case, it's not. How about number 3? Which side would be favored if I increase the volume? For number 3 here, the left side or the right side? Here, yeah, the left side would be favored, increasing moles of gas. For this reaction here, number 6, which side would be favored if I increase the volume? If I increase the volume here, it would be the right, yeah. Because on the left side, we don't have any gas. We only have 1 mole of gas on the right side. So increasing the volume will favor the right side. However, increasing the amount of calcium carbonate, which side would it favor? Increasing the amount of calcium carbonate would favor the right. This is a trick question because calcium carbonate is a pure solid. And what changes it is changes in concentration. Remember, for K, we look at concentration. And if the concentration doesn't change, then that doesn't change what we call its activity. And so here, increasing the amount of calcium carbonate, it's still 100% calcium carbonate, regardless if we have a little or a lot. We just need enough to reach equilibrium. And so it doesn't make it more reactive. This is different than something like, if you have 18 molar sulfuric acid versus 0.1 molar sulfuric acid, are they the same? 18 molar sulfuric acid and 0.1? No, not at all. But hey, what if I had 1 gallon of 0.1 molar sulfuric acid and versus 2 gallons? Would 2 gallons be much more reactive of 0.1 molar? No, it's going to have the same reactivity or the same activity. And so what's going to change that reactivity is going to be the concentration. So 6 molar would be more active. 18 molar would be more active. Okay, so I think we'll wrap things up. It's probably getting pretty late. And so we'll take a look at some more questions tomorrow night then. So in the case of solids and liquids, the amount can change, but not the concentration. Yeah, it's still 100% pure. And so if you add more calcium carbonate, the concentration is still 100%. And that 100% is going to be very reactive in that sense. Although it's a solid, solids in general aren't as reactive as liquids or gases because they like mobility. Solids have translational motion, but they don't have, actually solids do not have translational motion. Solids have vibrational motion. And whereas liquids and gases have translational motion, so they can move about and be more reactive. Okay. All right, then I'll post a link tomorrow and we'll do it at 10 p.m. tomorrow. We'll try to get through all the problems, I think, tomorrow. All right, good night. Okay, yeah, you're welcome, yes. See you tomorrow.